Number of connected components in an undirected graph. This is a premium medium problem. You have a graph of n nodes. You are given an integer n and an array of edges where edges of I is ai bi indicates that there is an edge between ai and bi in this graph. So we have to write down the number of connected components in the graph. So let's see this example here. We have 5 nodes 0, 1, 2, 3, 4 and these are the edges from 0 to 1, 1 to 2 and 3 to 4. So clearly we can see this is 0, 1, 2. This comes in one connected component and 3 and 4 comes in a different connected component. So there are two connected components. In the next example, you see there are also 5 nodes here, but there is only one connected component because all nodes are connected. So we can solve this problem using either a BFS or DFS based approach or using union find or disjoint set based approach. We'll see both here. So in the DFS based approach, what we'll do, we'll just create one adjacency list from the edges. So we had this edge, like 0 to 1 we had one edge, 1 to 2 we had a one edge, and 3 to 4 we had one edge. So 0 for 0 we have only one node in the adjacency list, that will be 1. For 1 there will be 0 and 2. For 2 there will be only 1. For 3 there is only 4. For 4 there will be only 3. And we'll keep track of one visited set. So initially we are starting with components 0, right? And then I will start DFS on any node. Let's say I'm starting from 0. So for 0, I will add it in my visited set. And then I will check its neighbors. Neighbors is 1. So I will try DFS on 1. So when I'll do DFS on 1, I'll add that in the visitor set and I'll check its neighbors. So 1 has 2 neighbors, 0 and 2. But 0 is already in visited. I will try DFS on 2. I will do DFS on 2. Here I will just add 2 in my visited set. So we'll go to the neighbors of 2. 2 has only one neighbor, 1, but that is in the visitor set. So we'll not do DFS on further. So we stopped here, right? So for when we started from 0, we traverse all this and we got one component. So as soon as we are done with one component, we can just increment our component counters by 1. Next, I will see if there is any okay, first we started from 0, we did DFS on that, then we'll do DFS on 1, right? But we'll not run DFS on 1 because this is already in the visited set. 2 is also in the visited set, will not run DFS on that. We'll run DFS on 3 because this is not in visited set. When we will run DFS on 3, we'll check 3 has only one neighbor, that is 4. We'll run DFS on 4. Before that, we'll add 3 in our visitor set. When we are doing DFS on 4, it has only one neighbor, 3, but that is already in the VFS step, so we'll not do it further. And also we added 4 in our visited set. So we'll stop our DFS processing here. And when we are done, again we'll increment our counter by 2. So at the end of this, at this point, we are done with 3 DFS of 3. If we start to do DFS on 4, we'll see 4 is already in the visited set, will not do any processing. So our components here will be 2. What is the time complexity here? Time complexity is for DFS, it's order of V plus C. V is the number of node and E is the number of edges. Okay, first we have to create one adjacency list. We have n nodes, so I need n empty list for each of the node. So this is basically a list of list and its size is n for n nodes. Next, I am going through the edges, A, B in edges. Both A and B are neighbors of each other, right? So adjacency of adjacent of A dot append B and ADG of B dot append A, right? So I have added B to A's adjacency list and A to B's adjacency list. Done. Now I have to write this DFS function. DFS function will take one node and a visitor set, and every time I'll be adding this node to our visitor set because we are visiting it. Next I will go through all the neighbors of this node, that will be ADG of this node. If this neighbor not in visited, then we have to visit, right? So then we will run DFS on that neighbor node and I will pass this visited. So that's it. That's the simple DFS function. And next I have to just call this DFS function. So for node in range n, I have to call this DFS function on node, but we need a visited set for that first, and we need the components. This is a variable I am just taking. So every time I am running a DFS on a node, so it will connect all the nodes starting from that node. So that will be for each DFS call there will be a component, right? So every time I'm calling this DFS, we have to check if node not in visited. If it is in visited, that means already some other node in some other DFS call from some other node, we have visited that node, right? So that's in some other component. So we don't need that. So if it is not in visited, then only I will run a DFS on that, and then I can increment these components. That's it. Next we can just return this components, right? It works and it's pretty efficient. Next is the next approach. Union find solution, we start with a parents list and a rank list. So let's say we have this 5 nodes from 0 to 4. These are the nodes, and initially each node will point to itself, like the parent of each node will be the same node, right? For 0, parent of 0 is 0, parent of 1 is 1, and so on. Also we are taking one rank list. Its rank list is basically the size of the component. So each node is a component initially. So initially there will be 5 components in this case, and each of the component will be of size 1. Next, we are starting with components 5, and then we will be just adding the edges. And how we will be adding the edges? Let's say we are taking the first is 0 to 1, 0, 1, right? So that means 0 and 1 is present in the same component. So we'll do a union operation on this 0 and 1, so that this two node will be linked. And I will come to that, like how we are linking it. But after this linking, just because we are getting rid of one node, right, one component here, so the components will be reduced by 1. So components earlier was 5, now it will be 4. Now next let's come to the union part, how we are doing the union. So the parent of 0 is 0 itself, and parent of 1 also was 1 itself, right? Both were separate components. So how do we decide if two nodes belong to different components or the same component? It's basically by the parent. If both have different parent, that means they belongs to different components. So initially they belong to different component because their parents were different. So let's say this 0 has rank 1, 1 has rank 1, right? So in this case, any 0 can point to 1 or 1 can point to 0, or we can say like 0's parent can become 1 or 1's parent can become 0. Let's say I am just putting it this way, 1's parent will become 0 in this case. So this is for the 0, 1 age. Next I am adding 1 to age. So after the previous operations, 1's parent was 0, right, and 2's parent was 2 only initially. right? So that means they both belong to different components. So we have to do the union. So how we'll do that? So we'll check the rank of both the parent. So once parent was 0 and rank of 0 will be 2, right? Because we just added 1 into this component. So the rank of 0 will be incremented. So I forgot to mention that in the previous computation. But rank of 0 will be 2 and rank of 2 will be 1, right? Parent of 1 is 0, rank of 0 is 2 and rank of 2 is 1. So that means 2 will point to 0. So 2 will point to 0 means we'll just get rid of this parent pointer and the rank of 0 again will become 3 because it is this component. The component starting from 0 is having 3 sides. Now one thing to notice here, I was adding the age 1 and 2. I could have just pointed this 2 to 1, right? So here we could have added this age, so parent of 2 could have become 1. So what was the problem there? There was no problem, but this is some optimization we are doing because we need a representative of this component. So let's say we need the representative is 0. For one the representative was 0. For 2 the representative was 2 itself. But if we just make 2.21, then fine, then we don't know, like 1 is also not the one's representative is 0, right? So we should have only one representative for all the whole component, right? So if that was the case, for if we just added one age here, so then to get the representative of this whole component, we had to first go to 1, then 0. This whole path we have to traverse for each of the further operations, right? So instead of that, if we can just directly point to this, like the representative, then it becomes easier. So we don't have to traverse all the path to go to the representative. Next we are adding 3, 4. So 3's representative is 3, 4's representative is 4. So we have to add them. We have to do the union. We can do anything like 4 pointing to 3 or 3 pointing to 4. Here we are doing 4 pointing to 3 because both have same rank or same size. Next we are adding, let's say next we are adding one more age, that is from 0 to 2, right? So what is the representative of 0? That is 0 itself. What is the representative of 2? That is also 0. So they belong to the same component. So we don't need to do any union. So in that case, we didn't reduce the component size. Now, basically we earlier also saw, like we started with a parents list and a rank list. Rank is always 1 initially. I'll just do this computation here once. Let's say I am first adding 0, 1. Right? So in that case, we'll just get rid of this, 1 will point here. So once parent will become 0 and this rank of 0 will become 2, right? Because 0 is representing one component that has size 2. Next we are adding, let's say 1 and 2. So once representative is 0 or parent is 0, 2's representative is 2 itself. That means we have to do the union on this 2. And how do we do that? Like the size of 1 is 1. No, we are just checking the size of the representative. We are not checking the size of this node. We are checking the size of this representative. That means the size of this component, right? So the component size is 2 here for 1 and component size is 1 here for 2. That means 2 will point to 0. So 2's representative again will become 0 and the 0's rank will become 3 because 0 is representing one component that size is 3. So this way we'll keep adding, and every time I am doing an union operation, I mean we need to do an union operation, we'll just reduce the component size by 1. If we don't need to do any union operation, then we'll return 0. Will not deduct from the components. Okay, first we'll take one parents list, or I can call it representative of the component. And first it will be I for I in range n, right? From 0 to n we have nodes, and each node is representative of itself. Next I will take one rank list as well, where rank of a free representative initially will be 1, like each has one size of 1. Next I will write one find function. It's basically to find the representative of the current node. So let's say I will take this node, and how do I find the node? So the node, while parent of node not equals to node, right? So we have to traverse. So earlier we saw that, so when we added 0 1 and 1 2, then 2 was pointing to 0, 2 will be pointing to 0, right? So find parent of 2, I have to run this while loop where we'll reach 0, then 0's parent is 0 only, right? So then this one will be the parent or representative. Sorry, I am just making mistakes here. Representative of node not equals to node, will just keep updating the node. What we'll do is representative of node will become the find of representative of node, because we are just trying to find representative of its parent or representative and the recursive way, and then we'll just update the node as representative of this node. So after this we can just return node, so this will be the parent or representative of this current node. Next I'll write this union function, so that will take two nodes. I'm just calling it AB because we have ages from A to B, that's what we are zooming, right? So we'll just find the representative of A and representative of B. How? Like we'll call this find with A and find with B, right? Fine. So now if representative of A equals to rep of B, that means both A and B belongs to the same component. We don't need to do any union operation, so we can return 0. Otherwise we'll check the rank, right? If rank of this representative is greater than rank of representative of B, that means, so if rank of representative of A is greater than rank of representative of B, that means the component that this rep A is representing has more nodes, right? So we'll make representative of rep B equals to rep A. So now also rank of rep A will be incremented by rank of rep B, because there will be only one component after this union, and the rank of that will be represented by rep A, and its rank will be incremented by the rank of representative of B. Otherwise we'll do this, we'll just do the opposite, and rank or representative of B's rank will be incremented by representative of A. That's it. And just because we are actually doing the union operation, we'll return 1, because the component size will decrement by 1. So initially we're starting with components n, because there are n components we are assuming, and then we are just for each age, for AB in ages, we'll just call this union operation of A and B, and that will return either 0 or 1, right? So we'll decrement the components by that. If we are not actually performing any union, then it will return 0, so we'll not reduce the component size, otherwise we'll reduce. So that's it, we can just return the components. There is some typo, I think. Yes, this works. Let's submit this. Right, this is quite efficient, and let's discuss about its complexity.